all. So in this video I'm going to work out the mathematics of how to figure out the photoelectric effect mathematically. So we start with a photoemissive surface and we have an incoming photon. That photon has a certain amount of energy. We're going to do everything here with electron volts because it makes so much sense. And the only challenging part mathematically, you'll see, is to convert electron volts to joules and then convert it to a frequency. We have simple formula to work with that, so that's not a big deal, but that is the hardest part we have here. So let's say this photon has 10 electron volts of energy. And here it comes into the photoemissive surface. Now, what's going to be emitted here? Well, there are electrons on this surface. They are bound to the surface with a certain amount of energy. We'll use electron volts to describe that energy. So consider an electron that is bound to this surface with 3 EVs worth of energy. Well, if I have an incoming photon with 10 EVs of energy, it's going to need 3 electron volts of that just to break the bond. Then the electron will go flying off. Question: how much energy will that ejected photoelectron, yeah, that's what we're calling it, an ejected photoelectron, how much energy will that have? You got it? We started with 10 EVs, we used 3 EVs to break the bonds. 7 electron volts of energy is what's going to be coming off. So this is an electron, right? This is a photon coming in, a chunk of light. We decided before that wave-particle duality. Hope you watched that video, and I hope your mind is a little bit blown with that. We've been amazed by that in physics for the last 125 years or so. That's the way the world works. So the electron, the photon comes in, it ejects an electron, great, uses up some of its energy in the process. 7 electron volts is left. So this is an electron. Got to remember that. Photon comes in and it ejects an electron. Okay, well, if it has 10 EVs of energy, we're going to want to know what that energy is in joules. And then we're going to want to know what frequency of light that is. Frequency is going to be measured in hertz. The units of hertz are reciprocal seconds. In other words, how many times does it vibrate per second? Okay. The joules is going to be a fabulously small number. The hertz is going to be a very large number. All right. So how do we do that? Well, to convert electron volts to joules, you multiply, not surprisingly, by 1. So let's do it. 10 electron volts. And if we look at our reference table, we can see an electron volt is 1.6 times 10 to the minus 19th joules. So 1 electron volt is the same thing as 1.6 times 10 to the minus 19th joules. That allows us to multiply by 1. So 10 EVs times 1. We're going to put 1 EV on the bottom, and that is equal to 1.6 times 10 to the minus 19th joules. This is a fabulously small number. So if you take your calculator, 10 times 1.6 EE, 19, don't forget to make it negative 19. If it comes out to be a large number, you know you forgot that one. That equals, not surprisingly, 1.6 times 10 to the minus 18th joules. So, very simple to calculate that. 3 electron volts is how much energy is needed to break the bond. We call this energy the work function. So the work function, measured in electron volts, well, we also want to convert it to joules. So how many joules is that work function? We're going to do it the same way. 3 electron volts times 1. So you have 1 EV down here, 1.6 times 10 to the minus 19th joules. So 3 times 1.6 EE 19 minus 4.8. So 4.8 times 10 to the minus 19th joules. Beautiful. So the work function is expressed in the amount of work, which can be both electron volts or joules. There's one other quantity we want to know here, and that is going to be something known as the threshold frequency. Now the threshold frequency will be, it's a frequency, so it'll be measured in hertz. That's simply how energetic this photon must be in its vibrations in order to eject an electron at all. The minimum amount, that's what this is all about, the minimum amount to break the bonds, but now we want to talk about it in hertz. We'll talk about that in a second. So the ejected photoelectron comes off with 7 electron volts of energy. We want to convert that to joules. Okay, we do it the same way as we did before. Okay, 7 electron volts times 1. 1 eV, 1.6 times 10 to the minus 19th joules. 7 times 1.6 EE 19 minus equals 1.12 times 10 to the minus 18th joules. That's how much energy that ejected photoelectron will have. So now we have our energies in both joules and electron volts for this thing. Question, is converting this to frequency, the electron, is converting that to a frequency useful? The answer is no. So these two are all we need for that. But for the photon ejecting that electron, we're going to have to get some units in hertz. Why? Because the photon has a particular vibration. That's where you would find out what the wavelength is as well, right? Find out if that's its frequency. So you know that its velocity is approximately c, and that would then give you its wavelength. But we really use this. We can figure out what color it would be and all of that. So how do we convert that? If we look in our reference tables, this formula right here, another derivation of that, I was just saying, C over lambda is going to be frequency. That's great. But this formula right here is the basic formula. Energy of the photon equals HF. Well, what is H? H is known as Planck's constant. And it's how we figure out, depending on what the frequency of the photon is, how much energy it has. So 6.63 times 10 to the minus 34th, and notice the units, joules, not per second, but joules times second. So let's work that. So we now have the formula E equals HF. You can see it's a very simple formula. We want frequency, so E divided by H will give us the frequency. So the energy is 1.6 times 10 to the minus 19th joules divided by 6.63 times 10 to the minus 34th joule seconds. If you look at that, joules will cancel. We'll end up with reciprocal seconds, which is going to be hertz. So while it's weird numbers, it's really simple calculations. So I'm sorry, this is 1.6 times 10 to the 18th joules. That's the number I'm taking here. 1.6 times 10 to the 18th joules is how much energy it has. So we're going to be dividing that. 1.6 EE 18 minus 1.6 times 10 to the minus 18 divided by 6.63 EE 34 negative. And that is 2.4 times 10 to the 15th hertz. 2.4 times 10 to the 15th hertz. And the numbers are always going to be something in this range, pretty much, just because that's where we have the light that we're generally playing with. Doesn't have to be, but it's not going to stray that far. 10 to the 14th, 15th, something like that. These always are going to be to the positive 15th. Imagine if it was to the negative 15th, that would be a rate of vibration that has not occurred yet in the life of the universe. So 2.4 times 10 to the 15th hertz. Down here we have 4.8. Okay, so let's get some space here. So E equals HF. F equals E over H. And the energy we have is 4.8 times 10 to the minus 19th joules. We're dividing that by 6.63 times 10 to the minus 34th. That's Planck's constant, and that's joules seconds. The joules cancel, leaving us reciprocal seconds, so we know we're doing it right. 4.8 EE times 10 to the minus 19th divided by 6.63 EE 34th minus, and that's going to be 7.2 times 10 to the 14th hertz. And that is all there is to that. So we'll work out some example problems, but this is how you do it. And I'll go over that kind of again in the next video. But we have an incoming photon of 10 electron volts. It smashes into an electron, which is bound with 3 electron volts to a photoemissive surface, the zinc plate, and it shoots out that electron. That electron would have all the leftover energy. So if it started with 10 EVs, the photon used up 3 EVs, you're going to have 7 electron volts left. Everything else is just converting those electron volt numbers into other quantities. So first we convert electron volts into joules, then we use E equals HF, using Planck's constant, to convert that into the frequency of light that would do that. We do that down here as well, but we don't need a frequency here because this is the ejected electron. So the frequency here is known as the threshold frequency, the minimum frequency to eject this thing. And the leftover energy is all in the electron. And the work function, which is very similar to the threshold frequency, the work function is how hard you have to work to rip that electron away. There you go. So it looks like a serious challenge. Once you get used to it, it's really not so bad at all. Let's try another example.